Hi all. In the previous lecture, we have seen that what is the motivation for us to define metric spaces in general. The stuff we can do are, we have reasonably explained that how or why that is the distance is a factor for which we can do it for a general set. And then we saw various examples on that. Okay. So now as we know the basic definition of metric space and I've seen examples to make ourselves comfortable, we can go to the structure or the analytical stuff what we can do in a general structure. Okay, so let's see that with examples. So in our second lecture, we are going to see stuffs like neighborhood, limit point, interior point, closed set, open set, and all, how we can define in general setup. Firstly, let us talk about neighborhood. Okay, so in the beginning you have to know that there is a set X and D. So this is a metric space. We have a metric space. Now we are going to do all the things. We are going to see what all we can do in the given metric space X comma D. Okay, we will not worry about what is X, what is D right now. We just have a metric space and we are going to work with it. So we have X comma D. Now we are going to define a neighborhood. So neighborhood is of a point. Okay, so this is how we write neighborhood. We know. So epsilon neighborhood of X. So where X is a point in X. So how we are going to define this? So we call it to be epsilon neighborhood of X around X. So we're going to define it like this. Okay. So this is our definition. This is a set of all y in X such that d of X comma y is less than epsilon. Just go back to the place where we defined the neighborhood on R, epsilon neighborhood on R. So there we have mentioned actually that how we define in the set theoretic form. So there it was just like X mod of X minus Y less than epsilon. So we did just this and we're just replacing mod of X minus Y less than epsilon by d of X comma Y less than epsilon here. Nothing else. X is replaced by R and d of X comma Y is replaced by mod of X minus Y. Then we'll go back to the definition what we did for R. So here goes the general definition. So any given metric space, we can define neighborhood like this. So this is actually the set of all points y in X for which the distance of y and X is less than epsilon. That is y is epsilon close to X. Okay, this is it. So this is how we define neighborhood. Good. Now we want to define limit point. So let me use the definition of neighborhood. Number 2. Limit point. Okay. So what about limit point? So what is a limit point? We told that for a general set subset of R, we have something called the limit point of the subset. We define that. That is, there should be a sequence in that subset which is converging to that point. That's it. So here also we're going to define like that, but in a bit different way. So given a subset of X, we will talk about the limit points of that subset A. So we say L, that L is also in X, is a limit point in X, limit point in A of A. So we say L, which is a element of X, is a limit point of A if for all epsilon greater than 0, there exists, let me phrase it like this, for all epsilon greater than 0, the neighborhood epsilon around L, okay, so this one, sorry, L minus L, this is something, and with this intersection of A is not equal to 5. So this might look a bit complicated. So just make the things easier. So what we're trying to say here is, okay, so this is called the deleted neighborhood. So let me just write it like this. So let me define it this. This is the deleted neighborhood around L. So we know what is a neighborhood around L. So intuitively, if L is here, we take all the points around L, which is epsilon close, right? Around L. Now this is the neighborhood of L, epsilon neighborhood of L. Now we just remove the point. We try to remove the point L. So we don't need the point L inside this. So that is something like the disk, and there is no this L thing. So this is not there. We call that to be the deleted neighborhood. So now for saying that L is the limit point of the subset A, we need to have this. That is for all epsilon greater than 0. The epsilon neighborhood, the deleted epsilon neighborhood of around L intersection A is non-empty. That for any epsilon greater than 0, this disk will contain some point of A inside it. There should be some point of A. Some point A which is in capital A. That should be inside it. That is what we mean by limit point. So like we can just take arbitrarily close disk around L, close neighborhood of L, but there also will find some point of A inside it. Okay. In the case of real, just go back to the case of real. What we defined in the case of real is just, let me just make this sure that you understand the analogy. So we defined if L is a limit point of the set A in real, then there is a sequence xn which is converging to L and never equal to L. That is same as saying that if we take any neighborhood around L, there is some point of A inside it. So in that way, we are saying that there should be a sequence xn for which xn is also like all the element of xn is in A for all n, and the xn is converging to L. It is same as saying that for any neighborhood around L, we have some point in A in that neighborhood, right? Just think about it for a bit. I think you will get it. So it is just the similar analogy we are doing here. So this is how we define limit point for a general metric space. Okay. You can also define a limit point by using the notion of sequence, but then I have to also define the sequence and all. So I'm not getting into that. At the last, we will define sequence on a general metric space, but then you can just go back and think that how we can define all these things, limit point, interior point, what we are going to define now by the help of sequences. Okay, that can be exercise. Let me clear the slide. Okay, let's just go in defining the interior point. So again, given a subset of X, so always we have this X comma D, a given metric space. So let A be a subset of X. We call X, so not X maybe, let me call it alpha, or what can be a good interior point? Let's call C. C in A to be an interior point. We call C in A to be an interior point of A if what happens? If there exists epsilon greater than 0 such that the epsilon neighborhood, so there exists, okay. I think we're comfortable with this, such that this thing is completely contained in A. That is, we are saying that there should exist a neighborhood around C which is completely contained in the subset A. So geometrically it is like if there is a subset A, all these points inside it are interior point. Why? Because you can take something like this. You can take a neighborhood around it which is inside it, right? But this point is not an interior point because there can't be any neighborhood which is completely contained inside this. And also this boundary here, if there is some point here, there also any neighborhood around it will not be completely contained inside the set A, right? So this is it. So this is called the interior point. This is an interior point. This is not an interior point. But okay, so let me say this. So this is, but this is a limit point, right? Because for any neighborhood around it, there is some point of the set inside it. So this set is A. So this is the set A. So for all neighborhood around this point, there is some point of A inside the neighborhood, right? So this is limit point, but not interior point. This is interior point and also limit point, right? This point is interior point and also limit point. And this outside point is neither interior point nor limit point, right? Good. So just try to think about them. Okay. So now we know what we mean by interior point of a subset of a metric space. And again, we know what we mean by limit point of a subset of a metric space. Now let XD be a given metric space. Let A be a subset of it. Now we claim that if A in A is not an interior point of A, then A is a limit point of A complement. So this is if and only if. Okay, we have to try to prove this. So this to make you used to the concept of limit point and interior point. I won't give a rigorous proof here, but I will give the intuition. You can just pause the video and try to solve it yourself. Okay. So for this direction, so A is not an interior point of A, right? So that means that if here there is A, if A is the interior point, then you should get a neighborhood around A which is completely contained in A, right? But we don't have that. That is, if we take a neighborhood around A, this neighborhood can't be contained completely in A. That means there should be a point here inside the neighborhood which is in A complement. And this is for any neighborhood around A. Because if for some neighborhood we don't have any point of A complement, then that neighborhood is completely contained in capital A, and hence A is an interior point of A, capital A. But that can't be the case. So for any neighborhood, we got a point of A complement inside that neighborhood. Thus, we can say A is a limit point of A complement. This is the forward direction. And let me erase this. And then again for the reverse direction. So if A is a limit point of A complement, okay, so then for any neighborhood around A, we'll get some point of A complement inside it. Some point of A complement inside it. Thus, no neighborhood around A can be completely contained in capital A, right? That implies A is not an interior point of A. So like this, you will try to find interior points and limit point of a subset of a metric space. Okay. So few notations. So let again, this is the basic setup we have. This is a metric space. And let A be a subset of X. Then interior of A, this is the set of all limit points of A. The set of, okay, so sorry, set of all interior points. A is an interior point. So this is what we define as interior of A. We call it as interior of A. And then we have this A dash, this. So let me use different notation. L. Okay, these are the notations we'll use. And again, another notation. This is the closure of A. This is called the closure. And this is defined as A union A dash. Okay. These are the notations we will use. And now we are ready to define open sets and closed sets. Okay. So in R, we know what do we mean by a open interval and a closed interval, right? So open interval is like, okay, so let me just erase this. In R, in our famous metric space, usual metric on R, so we call this to be an open interval, this to be a closed interval, and so on. So now we are going to define general open and closed sets on a general metric space. Okay, so here goes the definitions for open set. So here again, let X comma D be a metric space. If A is a subset of X, so for any subset of a metric space, we can mark them as open or closed, or like we can comment on their openness and closedness. So let us see this. So if A is a subset of X, we say A is open in X. Okay, so we won't mention this, but it means that A is open in X if interior of A is equal to A. That is, all the points in A are actually interior point of A. Okay, so we'll see examples. So for the first example, let's just verify that this holds for the open intervals in R. So for the first example, let's see this. So this is R on the usual metric. So is this an open set? So to verify this is an open set, you have to verify that all the points in this set are actually interior point of the set. So now take any point in this set. Take any point in this set. So this point should be interior point of the set. And why is the interior point? Because you can take a neighborhood around it, a small neighborhood around it, such that the whole neighborhood is actually contained in the interval 0, 1. And you can do this for any element in the interval 0, 1. Thus it is an open set in R. Now let's just take this in R again. So is this an open set? No. This is not an open set. Why? So 0 is a, so if we have to say this set is not open, what we have to do is we have to come up with some element of the set which is not an interior point of the set. As simple as that. So now we get the point 0. So what about the point 0? 0 is in the set. 0 is in the set close 0, 1. 0 is in the interval of close 0, 1. But is 0 an interior point of this set? No, right? Because any neighborhood around 0 will contain some outside points. So none of the neighborhood around 0 will be completely contained inside the closed interval 0, 1. Thus, we can conclude that 0 is not an interior point of 0, 1. Thus, interior point of 0, 1. Okay, so 0 is not an interior point of 0, 1. But 0 is in closed interval 0, 1. Thus, this is not open. So for now, we don't know it is closed or not. We just know, given any subset of a metric space, we can comment on their openness and closeness. So for now, we can just comment on their openness. We can say it is open or not, right? So it is not open. We'll see other examples also, but let us define the closed set also first. Also, I will clear the canvas. Let's go to closed sets. Again, we have the general setup. X comma D should be a metric space. A subset of X. Now, we say A is closed. Specifically, we can say in X if A dash. So all the limit points of the set should be inside the set. That is when we call the set to be open. Sorry, closed. Okay, this is a definition of closed sets. Now let us just see a few basic examples. So first, our well-known closed interval in R. So is this closed? Yes, because, okay, so what are the limit points of the set? So we have to just make sure that there is no limit point outside the set. So this is set 0, 1. So any point outside the set will be here or here. Now this point can't be a limit point of the set 0 close 0, 1, right? Of the interval close 0, 1. Because there are, so we can take neighborhood around this where there is no point of close 0, 1 inside the neighborhood. So thus intuitively we can be sure that here also you can take neighborhood like this where there is no point of close 0, 1 inside the neighborhood. Thus we can know any point outside the closed interval 0, 1 will have such a neighborhood around it where there is no point of our close 0, 1. Thus none of the points outside this set can be limit point of the set. Okay, so this is closed. Now let's just take the example this. So we already knew that this is not open, and now we know that this is closed. Okay, so now let's just take this. So is this closed? Okay, so to say a subset is closed, we have to make sure that no point outside it can be a limit point of it. And to conclude the subset is actually not closed, we have to have a limit point of that set which is outside the set. Then we can say that set is not closed. So here we get 1 to be such thing. Okay, so let it be 0, 1. We can say, okay, so what about 1? Is 1 a limit point? Is 1 a limit point of this open interval 1, 0, 1? Yes, right. Because any neighborhood around 1, you will get some point of open 0, 1 in that neighborhood. And similarly for 0 also you can do that. So any 1 will, for if we get 0 or 1, it doesn't matter. So for both 0 and 1, for 0 also, if we take any neighborhood around it, you will get some point of open interval 0, 1 inside it. Thus 0 is a limit point of 0, 1, and also 1 is a limit point of 0, 1. But none of 0 or 1 is actually inside the set. So there are limit points of the set outside the set. Thus this is not closed. And also we know this to be open, so it is open and not closed. So these are the basic examples of open sets and closed sets in our general, like, specific setup of R. We will see other examples also. But what you can do now is just revise the definitions of open sets and closed sets. That this is going to be very useful, for the study. And now we are going to see a few examples for it. Okay, so first let's work on our general, in our mostly work situation, that is usual metric on R. Okay, so here what about this set? So is this set open? So first let us talk about its openness. So this is example 1. So is this set open? This is not open. Why? So again, if we want to say that this set is not open, we want to get a point inside that set which is not a interior point of the set, and here that is 0. So this set is like this. Now what about 0? 0 is a point inside the set, but it is not a interior point of the set, because if we take any neighborhood around 0, there will be some point outside the set. So none of the neighborhood around 0 will be completely contained in the set. So let this be set A. So it won't be completely contained inside A, any neighborhood around 0. Thus 0 is in A, but 0 is not in interior point of A. So 0 is not an interior point of A. Thus it is not open. Now what about closed? Is it closed? Again, it is not closed. Why? Because if we get a point outside the set A, which is a limit point of the set A, then we can say it is not closed. And here it is 1. So 1 is not inside the set A, but again for any neighborhood around 1, you will get some point inside the set A. So thus 1 is a limit point of the set A, but 1 is not in A. So 1 is not in A, but 1 is in A dash. Thus this is not closed. So again, we got a result or a fact maybe. So there can be set which is neither open, neither closed. So there is nothing to worry about if we come around with a set which is neither open nor closed. It can happen. Okay, good. So let us go to example number 2. Again, we are working on RU, the usual metric on R. So what can you comment about this? Rationals. What can you comment about rationals? So is it closed? And then again we have, is it open? Two questions. So the answer is, it is not closed, it is not open. Why? Okay, so the rationals numbers are like, we can't just make it very clear, but it is like this. Okay, so there are infinitely many rational numbers and there are countably many, but yeah, so they are very much close to each other in some sense. Okay, so but why it is not closed? Because let us take any rational number. So let's just take 1. No, so to say it is not closed, let us take any irrational number. Let's say root 2. So root 2 is not in the set of rationals, right? But take any neighborhood around root 2. There will be many rationals in that neighborhood, right? Any neighborhood around root 2 will contain some rational number. Thus, root 2 is a limit point of the set of rationals, but it is not actually in the set of rationals. So thus it is closed. It have a limit point outside the set. Thus it is closed. Now, okay, so now to comment on whether the set is open or not, let's just check the point 0. Okay, so 0 is in rationals. 0 is in rationals. But is this a interior point of the set of rationals? No, right? Because take any neighborhood around it, there will be some irrational point in it. Some irrational point in it. Thus, 0 is not in the, like 0 is not interior point of rationals. Thus, it is also not open. You can just similarly check that irrationals are also neither open nor closed. Again, natural numbers are also neither open nor closed. Okay, good. No, natural numbers are actually okay. So let us see what natural numbers are. Okay, so I told something wrong. Maybe I was not very cautious here. So let's just see what the set of natural numbers are. So you can just check that similarly for irrationals, it is neither open nor closed. So what about set of naturals? So is it closed? Yes. Is it open? No. So why, firstly, to see why it is not open, just check any natural number for 1, let's say. So 1 is a natural number, set of natural numbers, but take any neighborhood around 1. So there are infinitely many other numbers, right? So numbers which are not in natural set of naturals. Thus 1 is not an interior point of set of naturals. Thus this is not open. So we find a element inside the set which is not an interior point of the set. Now why the set of natural numbers is closed? Okay, so it is a good question to ask. So just see what the set of natural numbers is. 1, 2. So to show that it is closed, what we need to have, any point outside the set can't be a limit point of the set, right? So just check any point here or here. So you can find some neighborhood around the point which doesn't have any natural number, right? Again, for this you can do that. So for any point outside the set of natural numbers, you can find a neighborhood around it which doesn't have any natural number. Thus we can say that the set of natural numbers is closed. Okay. So just, it is a matter of fact to check that a dash is actually 5. So there is actually no limit point of the set of natural numbers. And the definition of closed set is it should be A dash is subset of A. So it is not only subset of A, it is actually a null set. So it will be in any case subset of A. Good. Okay. So we are done with example 3 here. So let us go to some other metric space. So we know fairly about the real usual metric on R. So we can see how the things changes drastically if we change the metric space. So let us consider R. Let us consider R under the discrete metric. Okay, so discrete metric. So what is a discrete metric? Just recall. So here dxy is equal to 0 if x is equal to y and 1 if x is not equal to y. So what about, so my claim is, so we know what we mean by open set and closed set for any metric space. So now we have a metric space on R which is different than the usual metric. In usual metric we saw that how we can say this set is open, this set is closed, and so on. Okay, good. And one more thing. Okay, so just go back to the usual metric in R. So what about in usual metric in R, what about R? So R is both open and closed. Both open and closed. Why? So take any point in R, that is the interior point in R, right? Because any neighborhood around it will be subset of R. So that is why it is open. And again, why it is closed? To be not closed, there should be some point outside R, which is the limit point of R. But the whole set we are working on is R. So we can't find any point outside R only. So there is no question of that point to be a limit point or not. So again, it is closed. So it is trivially open and closed. And again, if you consider the set phi, it is both open and closed. Okay. Okay, so let's just see this discrete metric on R. So it is interesting actually. So my thing is, I will claim that take any subset of R. Now we are working on the discrete metric on R. So any subset of R will actually be both open and closed. And why it is so? Just think about it, why it is so. Okay, fine. So let's just first think about interior points of A. Now to be interior point of A, it should be the case that any neighborhood around it will contain, okay, so there exists some neighborhood around that point. So if A is the interior point of capital A, then there should be some neighborhood around small a, which is completely contained in capital A. So, okay, so I claim that interior point of A is equal to A. So for that we have to take any A in A. We need to show that this A, small a, is an interior point of A. Now take the neighborhood half around A. So that is the set of all points for which the distance between A and that point is less than half. So now that will only be the point A, right? Because any other point will have the distance 1 with A. So there can't be any point with less than half distance and not equal to 0 distance. So if there is any point which is less than half distance with A, that should be 0 distance with A, and that is only the point A. So this is obviously a subset of A. Thus interior of A is actually equal to A. Thus this is open. This says it is open. Now for closed, you have to check that any limit point will be inside the set. Okay. So we can just think about A dash, set of limit points of A. Now what is actually this? So just try to think, what is this? Okay. So this is actually phi. So there can't be any limit point of A. Right? So why there can't be any limit point of A? Take any point in this discrete metric space. So now if we take the, okay, so to be a limit point, it should happen that in around any neighborhood, in any neighborhood around A. So suppose, so let's say assume the contradiction. Suppose it is not phi. Let there exist some point which is in, so let's make it L, which is actually a limit point of A. But in that case, for all neighborhood around L, there should be some point in that neighborhood, like not in that neighborhood, in the deleted neighborhood, like you can't consider L. So, okay. So there should be some point in the deleted neighborhood around L, which is in A. But again, if you take the half neighborhood of L, that will be only L. So the deleted neighborhood, deleted half neighborhood around L will be actually phi. So you can't find, so if it is a limit point, then for any neighborhood around it, you should find any deleted neighborhood around it, you should find some element of A. But you can see the deleted neighborhood around L, deleted neighborhood half around L is actually phi. So there is no point of A inside the deleted neighborhood of L for epsilon equal to half. Thus, there can't exist such L. Thus, this is phi. And if this is phi, this is obviously a subset of A. Thus, this is closed. So any subset of R is open and closed both in case of the discrete metric on R. Okay. So as we change the notion of distance, there is something to notice. As we change the notion of distance in a set like R, we took the notion of distance, the usual notion. Then we got some sets to be open, some sets to be closed, and so on. But when you change the notion of distance, then the whole concept of openness and closedness is changing. Right? Now all sets are open and closed, but that is not the case in RU, the usual metric on R. Okay, so that is something to observe. Okay, so one more just notation, like not notation, definition. So we call the sets to be clopen if they're both closed and open. Okay, then we call the sets to be clopen. Good. Okay, so now we can define. Okay, so let me, okay, so another definition. So we know fairly about open sets and closed sets now. Okay, so let us just prove one theorem. So I will highly suggest that try to prove this theorem by your own. Pause the video and try to prove the theorem. Okay, so the theorem says if A, and now in the general setup we have X comma D to be a metric space. I won't write it again and again. And A is a subset of X. And now here X is a metric space. Okay, if A is in X, A is open if and only if a complement is closed. This is in any general metric space X. Okay, let's try to prove this. Okay, so let us prove this. So for this direction, for the forward direction, we need to show that, we are assuming that A is closed. We need to show that A complement is open. Required to prove its complement is open. And for that, we have to prove that for all X in a complement, X is in interior of a complement. That is, X is an interior point of a complement. So assume not. So assume the contradiction. So that is, there exists some X naught in a complement such that X naught is not in interior of a complement. That is, X naught is not an interior point of a complement. So when do we call X naught to be an interior point of a complement? When there is some neighborhood around X naught, like for some epsilon greater than 0, that epsilon neighborhood of X naught will have all the points inside a complement. That is, the neighborhood will be subset of a complement. So now X naught is not an interior point. That is, for any neighborhood of X naught, any neighborhood around X naught, like none of the neighborhood around X naught can be totally contained in a complement, right? That is saying that any neighborhood around X naught will have some point of some point which is not in a complement, that is in A, right? So for every neighborhood of x0 there is some point which is actually in A, that is not in a complement. Thus we can say x0 is a limit point. Okay, and now x0 is also in a complement. So that point which is in A can't be x0 itself. So that point is in the deleted neighborhood of x0, right? Thus from here we can say x0 is a limit point of A, right? But x0 is not in A, and this contradicts our assumption that A is closed. For a closed set, all the limit points should be inside the set. But here, x0 is a limit point outside the set. Thus, that is a contradiction. So, a complement is open. Right? So, this was our forward direction. Okay. So, let's just go to the, try to prove the reverse direction. The proof is quite similar. Okay. So, now we assume that a complement is open and try to show that A is closed. For that, we need to show that all limit points are inside the set of A. Like all limit points of A are inside the set. So again, assume the contradiction, suppose not. Suppose not. That is, there exists some L, which is a limit point of A, but L is not a limit point of, like L is not in A. So if L is not in A, then we can say L is in A complement. Now L is in A complement and L is a limit point of A. That is, for all neighborhood around L, there is some point of A complement inside it, some point of A complement inside it. Thus, L can't be an interior point. L is not an interior point of A complement. So from here we can say, from here, so using this, we can say L is not an interior point of A complement. Now L is in A complement, L is not an interior point of A complement. From there we can say A complement is not open. But that is a contradiction because we know by our assumption A complement is open. So this is the contradiction, as A complement is open. So similar proof for the reverse direction also. So we have proved that is A is closed if and only if the A complement is open. So this is a very strong thing to say. So given any metric space x comma d and any subset A in X, we can say about the open or closeness of a set if we know the open or closeness of its complement. Okay, so that's it. So this was more or less a discussion on open and closed sets, and including the discussion on interior and the limit points. So these are very important stuff doing in a being in a metric space. Okay, so okay, good. So let us see another definition, another important definition. So we are more or less done with this open set closed set thing. So you can go through examples, like just think about any metric space you know, and then just try to discover the if a subset of it is open or closed. So just try to think about different things. You can do it here. So now let us define this. So what we are doing now is just defining various stuff on a general setup of metric space. So now let us define another thing, bounded metric space. Okay. So what is bounded metric space? So let x comma d be a metric space. We call it bounded if there exists x naught in X and R, let's say R naught in the set of R such that x is, okay, so let's say x is equal to ball of radius r naught around x. And we are considering this ball inside, this ball is inside x. This is a very motivated definition. So we call a set to be bounded if there exists, so if this is a set and there is a point x naught such that there is some r such that r neighborhood around x naught is the set, then we call it to be bounded. And if it is not bounded, then it is we call it to be unbounded. So again, note x is unbounded if it is not bounded. Okay. So for a very trivial example, our famous metric space, that is the usual metric on R, is not bounded, right? It is unbounded. So examples. So let's see this. This is the usual metric on R. So this metric space is unbounded. Okay, so let's see RD. There is a discrete metric space of R, and this is bounded. Why this is bounded? Just take, so why this is bounded? Just take anything like this. So that is a set of all points x in R such that d of 0 comma x is less than 2. Now d of 0 comma x is either 0 or 1. So these are discrete metric space, which is giving the distance to be 0 if the points are equal, and if the points are not equal for two different points, it is giving the distance to be 1. So now it is less than 2 for any x, right? So this set is actually equal to R. Thus this set is bounded. This metric space is bounded. So just one thing to note. So in a particular set, we can define two different metrics such that one metric space is bounded and another is unbounded. So bounded and unbounded is totally dependent on the notion of distance on a set, not only the set. Okay, just think about it. Good. So another very important definition I want to make here. So not only here, so this is another general concept. So this was like more or less about the bounded metric space. Now let me define this. This definition is on subspace matrix. So we could have defined it earlier. Okay. So what is subspace matrix? So suppose x comma b be a metric space, and let A be a subset of x. Then we want to define a metric space on A. So we define it as A comma D, where D of like this D, let's call it D tilde. So D tilde of A1, A2. So A1, A2 are points in A is equal to D of A1, A2. So D is here, this D is here. This is just a subspace matrix. So we are just taking the projection on A, a subset of X. This is also a metric space. So if X is a metric space or any subset of A, we can have a metric space with the same notion of distance. Right? Good. So for example, so we know our usual metric RU. So let's take this open interval as a, so just define the metric space on it. So this is a metric space, the subspace metric. So let this be a, so let's consider the subspace metric of A, that is the metric space having the set to be open interval 0, 1, and the metric on it, the notion of distance on it to be the normal notion of distance of R just made to the projection. Okay, so then this is also a bounded metric space. So just one thing to note: if we are given a bigger matrix space, so let's we are given a matrix space X, then from the first place there is nothing like we can't say anything about bounded or unbounded thing of a subset of it, right? Because bounded or unbounded is defined on a complete metric space, not a subset of a metric space. So for now, like from the initial definition of boundedness, there is nothing. We can't say anything about boundedness of uh, open interval 0, 1 or closed interval 0, 2, something like that, or n set of naturals or q, because this is a property of a metric space. But now what you can see from this is that for any subset of it, you can just define a subspace metric such that that subset is a like the subset is forming a metric space under the same distance, notional distance of the bigger set. So in general, like with some loss of like with a bit of ambiguity or a bit loss of rigorousness, we can just extend the definition to the subsets of a metric space also. So now it does make a sense to talk about boundedness or unboundedness of a subset of a metric space, because maybe subset is not in at the first place a metric space, but you can define a metric space on it in a quite similar and quite easy way, and then we can talk about its boundedness or unboundedness. So that's what we mean by saying that this subset of this bigger metric space is bounded or not. Okay, so this was it. So I think we are almost like quite done with having discussion on things we can do on the metric space. So again, so let me just end it with the analogy with R and just give you things like sequences. So sequences we can define in metric space also, right? So let x comma d be a metric space. Then let xn, we call this to be a sequence if x is in x. So this is a sequence in quite simple definition. Sequence in x comma this metric space. Okay. So when is the sequence convergent? When we call the sequence to converge, so okay, so let me write this definition. So xn converges to a as n tends to infinity, and here a should belong to x if and only. So here goes the definition. If and only if distance of xn comma a goes to 0 as n goes to infinity. Okay, so now okay, so let's with a given sequence xn in capital X, we can generate a sequence d of xn comma a, and suppose xn is given and a is given. So xn sequence in capital X is given, a element of x capital X is given. So we can define a sequence xn comma a. Now this sequence is a sequence in R, so this is a real sequence, and we do know about the limit of a real sequence, and we do know the sense of like the meaning of saying that this sequence converges to 0 as n converges to infinity, n diverges to infinity, like n tends to infinity. So we define this xn converging to a as n tends to infinity if the real sequence d of xn comma a is going to 0 as n tends to infinity. In other terms, you can also write it like this. This happens if and only so you can try to prove the equivalency of them. You can write it like this also: for all epsilon greater than 0, there exists capital N, which depends on epsilon obviously, in the set of naturals, such that d of xn comma a is less than epsilon for all n greater than equal to n epsilon. This is also equivalent form of writing it. So just try to check their equivalent, like they're the same. So we can talk about convergence of a sequence. Similarly, we can talk about like not convergence of a sequence. We can talk about bounded sequence. We can talk about unbounded sequence. We can talk about subsequence. All the things are we can do it in a similar manner. So again, the same manner. Okay, so let me just erase this. So what all we can do now? I will not write it completely. So in R, we can define continuity by sequences. So similarly, in X comma D, a general metric space, we can do so. So we can have definition of continuity by sequences. We can have definition of limit by sequences and all that. So this was more or less a discussion about things we can do on a general setup. So let us just go back to the slide and then we'll see a very interesting. So what all we can do in a metric space? First we know that, okay, so first we know what do you mean by neighborhood of in a general metric space. We know what do you mean by limit point. We know what do you mean by interior point. We know what do you mean by closed set, open set, bounded set, and we did analogy with R. So we did stuff. We did quite a lot of stuff. So this is enough to know, like for the initial study, we at least know we can do all such analytical structure. We can have all such analytical structure, more or less all the structures we had in R, we can extend it to a general metric space. Okay. So one more thing to note, we can't do this differentiation thing. So differentiability and integrability is a bit more complex thing. So for integrable and stuff, there are something called measurable spaces. So that is not exactly the same as a metric space. So in a general metric space, you can't be able to do integration and differentiation and stuff. But till continuity, everything is okay. We at least know that. Okay. So then we will do a very important thing. That is, so we'll prove this for R and just try to do this for a general metric space. So the proof are quite same. So if we just try to order it with the order of difficulty, let's say, or the complexity of the proof, then it's actually the same if we try to prove it for R and if we try to prove it for general metric space. The notation will change. But this as exercise, I will give you the proof in R and just try to generalize it for the general metric space. Okay. So the theorem goes. So one very interesting thing we will do about continuity here. So let's say f is from R to R, continuous. So this is if and only if for all open set O in R, f inverse of O, so open, f inverse of O is also open. Okay, what is f inverse of O? F inverse of O by definition is all x in R such that f of x is in R. This is the inverse image of a function. This is not that bijective inverse, okay? So this inverse acting on a subset of R, subset of the codomain. So this inverse exists for any function f. It doesn't have to be bijective. So just go through the definition to make yourself comfortable with this. So this is our claim, and we are going to prove this. And we can do this for general set x, and again we know what we mean by open in a general set x, and then again everything we can do it for x, where x comma d is the metric space. Similar proof, but now we are going to do it for R, and leave us exercise for the general. So you can wait for, like, you can just pause the video for 5 minutes, and just think about it. I'm going to discuss the solution. Okay. So now we are going to, okay, so let us do this direction first. So if this is continuous, then it should be open, right? Okay. So let's assume the contradiction. That is, f is a continuous function, but there exists some open interval where it is not open. Or okay, so let's just drop this contradiction thing. We can do it directly also. So to prove this to be open, to prove f inverse of O is open, what we need to prove? We need to prove any point of it, any point in it. So let x be in this. Then x is also in the interior, like x is also an interior point of f inverse of O. Okay. So if x is in f inverse of O, that implies that f of x is in O, right? That's by definition of f inverse of O. So if x is in f inverse of O, then f of x is also in f inverse of O. And if f of x is in f inverse of O, if this is the case, then let's say f of x is this. So okay, so good. Now O is an interior point. So like O is an open set, right? So O is an open set by our assumption. So O is an open set. Thus f of x is an interior point of O. Thus f of x is an interior point of O. Right? Thus, from here we can say, there exists epsilon greater than 0 such that f of x minus epsilon to f of x plus epsilon is completely contained in no, right? Now again, by continuity of f, now f is also given continuous, we have delta such that f of x minus delta to x plus delta is completely contained in f of x minus epsilon to f of x plus epsilon. So maybe this proof is becoming a bit of clumsy here because there is not much space in here. But okay, so after this line, we're going to this line. And if this is the case, then we are just getting that this should be a interior point. Because for around x also, so why is the interior point? So now if you take this, and this is also subset of O, so we already proved that x is an interior point of this. Because we have some delta such that x minus delta to x plus delta, this complete thing is inside f inverse of O. Right? There exists a delta such like there exists a neighborhood around x such that the whole neighborhood is inside that set. In this case, that is f inverse of theta. So thus we know that f inverse of theta is indeed open if theta is open and f is a continuous function. Good. So let's just erase this and try to prove the converse direction. Okay. So now proving the converse direction. Now what we need to show that if this is the case that for all open set O in R, if inverse of O is also open, then that f should be a continuous function. Okay. So to show the function is continuous, we need to show that f is continuous. So RTP required to prove f is continuous at, let's say, A in R. F is continuous at A in R, and this we can do for all A in R. So it is continuous at each point. Then we call the function to be continuous. So for a given, so let given A in R, we need to show f is continuous at that. Okay, so what do you mean by continuity? For all epsilon greater than 0, there exists a delta greater than 0 such that if x minus a is, so if x is in a minus delta to a plus delta, or we can just write it like this, f of a minus delta to a plus delta is subset of f of a minus epsilon to f of a plus epsilon. Okay, good. So now we have to take this. We have to prove this. We have to prove this. But now what we are given, what we have is if theta, if phi, O is open set, like if O is open set in R, then f inverse of O is also an open set in R. So now take O to be. So we are going to have the proof. So let's just erase this part. So let's say, let's take O to be f of a minus epsilon to f of a plus epsilon. Right? So now this is an open set. So f inverse of O is also open in R, right? That is by our assumption. Again, A is in f inverse of O, right? A should be in f inverse of O. Why? Because F of A is obviously, so this trivially that A should be in F inverse of A. Thus, from here we can say A is an interior point of F inverse of A, right? Then again, we need to erase this. So now if A is an interior point of F inverse of O, if that is the case, then there exists delta greater than 0, like there exists a neighborhood around A which is completely contained in F inverse of A. So there exists delta greater than 0 such that A minus delta to A plus delta is subset of F inverse of A. That again implies F of A minus delta to A plus delta, there exists such delta is inside O. And now what is O? This is our F of A minus epsilon. This is exactly what we want to prove, and thus we are done. So thus we know that the function is continuous at A. And now we can do it for any A, thus the function is in general continuous. So what we did now is exactly we came up with a condition of continuity by the notion of open sets. So now we can check a map from a set like from R to R to be continuous or not by just seeing the inverses of open sets of R, open subsets of R. So we take the F inverse of all the open subsets of R, and if they are all open, then we can say that it is continuous and vice versa. So this is a very strong condition. Only knowing about how the function works on the open subsets of R, we are able to guess if the function is continuous or not. And just try to do it for the general metric space x comma d, and you can do this, right? So just replace all these such intervals to be a ball of epsilon around F of A or around A. So just replace with the trivial things and you will get the general proof, and that is not a bit more difficult from this. So they're exactly same. Now thus for a general metric space, we have the definition of continuity by just using the notion of open set, by just seeing how the function works on the open sets. Okay, so that's a very good observation again. So let's just go to the slides back and then have a quick discussion. So this was about continuity. Okay, so now what we are going to do is we are going to end our lecture in a very interesting way, like I tried to make it interesting. So as promised, we will have the glimpse to topology. Okay, so for metric space we only need a notion of distance. So from the first, what we did, we first tried to do analytical stuff on R, on the set of reals, and then we understood that mostly the things we are doing there are dependent on the notion of distance. So if we know the distance between 2 points in a general set X, then there is no reason why we can't do the same in that set. Thus, we did have we defined a metric space, and then we did have a discussion on their properties, and we saw that how exactly most of the properties, like till the continuity stuff, sequences continuity and all, limit point, open sets, closed set, we can define it for a general metric space that is just only having the notion of distance. We don't need to have 2 times 2 is equal to 4 or any other properties of R. So we just need to have that thing called distance. Now we again just saw that there is another vision coming. So this continuity thing, we also don't need distance to define continuity. What we need is a notion of open set and checking the function on the open set. So that is, in a nutshell, the notion of open sets. So if in a general set we are given the notion of open sets, then we can just have the notion of continuity. We can just define continuity in general set. And this is more generalized than metric spaces. So why? That is something you can ask yourself. So that is, just try to think it like this. If you are given a metric space, then we know what do you mean by open sets in a metric space. But you can't go back. If you are given like this sets are open, then can you just trace back to a definite metric space on that set? Can we? The answer is no. That is not our topic of discussion here, but whatever, you can just intuitively feel that this, if we just only have the notion of open sets on a general set X, that we only know that these sets are open. We don't know the distance between 2 points or any other thing. We just know that these subsets of this set are open. We just know that. So that is a bit more generalized than knowing the distance between two exact 2 points. Okay. And two more you can say exercise for you guys. Uh, you can just try to check this, and this true for R, this true for any general metric space. So arbitrary union of open sets are open. So you can take arbitrary union of open sets, and that will turn out to be open. And you can take finite intersections of open set, and that will also be open. Okay, there to just properties to check. You need to check them, and that is not very difficult to check. And again, for closed sets also we have such stuff. Like for closed sets, the finite union should be, the finite union is closed, and the arbitrary intersection of closed sets should be closed. So there's a property we have. Now keeping that in mind, we define topology of a set. So I will just end this lecture giving you the definition. I won't explain it further. It requires a bit of time that we don't have right now. Okay, so let X be a set and let T or tau be a family of subsets of X. Then tau is called a topology on X if, first condition, both the empty set and the set X, like both the empty set and the whole set, are elements of tau. Any union of subsets of tau is an element of tau. So what again, and this is end it, any intersection of finitely many elements of tau is an element of tau. So we have a general set capital X. Now we have a family of subsets of capital X. That is, we take the power set of capital X and take a subset of power set. That is tau. Subset of power set means we are selecting few subsets of capital X. And in the selection, there should be few points to be clear, like few points to be satisfied. That is, in the selection, we need to select the whole set X and the empty set. If we select few elements and few subsets of X, and the union of the subsets should also be a, we should also select that. Any intersection, finite intersection of subsets we selected should also be selected. Okay, that in that manner of selection, if we select few subsets of X, capital X, and we end up having a collection of subsets, family of subsets, tau, then we call tau to be a topology on X. And then this pair X comma tau is called a topological space. Okay. Good. So this was the definition. You can just, if you're interested, you can just ask your mentor or get back to me regarding the sources. So for general, you can just, like general metric space and all we discussed earlier, you can just study the famous Baby Rudin, the Walter Rudin principles of mathematical analysis, and also you can study glimpse to topology in the Bartlett-Shepard analysis or something. There is a book, Bartlett-Shepard. Or otherwise, you can just go to your mentor or ask me personally if possible, if you're interested to study about this topology and metric spaces and their link in more detailed manner. Hope you all enjoyed the class. Thanks for being here with us. Okay. Okay. Bye.